Before I start to talk about my experiment, I would like to begin to acknowledge that the land used in the experiment is on Mi'kma'ki territory, which is the land of the Mi'kmaq people. My research question for this experiment was, do snails in shallow tide pools move faster than snails in deep tide pools? This experiment was conducted on Monday, June 3rd at the Bay of Fundy, Rocky Beach in Margarettsville. This is approximately a 2-hour drive from Dalhousie University campus. Here is a map of the location that Experiment 2 was conducted in. It is in Margarettsville, which is about 20 minutes from right outside of Kingston and approximately 2 hours away from Dalhousie University. The red dot is approximately where the experiment was taking place, right on the Bay of Fundy. For my experiment, we used the species Littorina littorii, which is a common periwinkle, and this is the most common snail found on the beach. It is a type of snail with a spiral shell that comes to a point, and it is usually colored with gray, green, or brown, and they are commonly found throughout the North Atlantic, prominently in tide pools or along rock crevices. So they were a very prominent species at the beach that I was at. For my methods, I did snail tagging, temperature measurements, and snail tracking. Snail tagging was to determine how far and fast these snails moved within a certain amount of time. I tagged them by painting their shells. This is the picture that you see on the right. I took 8 different colors. So the first part of the experiment involved measuring the depths of the tide pools. I considered tide pools with the depths of 2.5 centimeters to be shallow, and those with the depths of 10 to 15 centimeters to be deep. The shallow tide pool had a depth of 2.3 and dimensions of 24 by 20 centimeters, while the deep tide pool had a depth of 12.5 centimeters and in dimensions of 55 times 95 centimeters. For temperature management, I measured the temperature in both tide pools using a waterproof thermometer. The shallow tide pool had a temperature of 22.9 degrees, and the deep tide pool had a temperature of 19.6 degrees. For snail tracking, I removed 8 snails from the center of each tide pool, dried them off, and painted their shells with nail polish. After allowing the polish to dry, I placed the snails back in the center of the tide pool with the corresponding colored rock. I then timed the snails for 30 minutes to allow them to move around. After the time elapsed, I used a ruler to measure the distance from the color rock to the matching colored snail. The data collected will be summarized in the table. Before we go into the data and results, I thought I would go over some materials that I used through this experiment. The first one being my iPhone. I used this for the photos and GPS along with the iNaturalist app. I then used a ruler to measure the depths of my tide pool, waterproof data sheets along with a pencil, first aid kit that did not get used, a iNaturalist guide along with 8 nail polishes to tag the snails. I then had this all inside a water-safe bag and wore waterproof shoes so my feet didn't get wet walking through all the tide pools and on the beach. Looking at the results, looking at table 1, the shallow and deep tide pool physical traits, the shallow tide pool measured 2.3 centimeters deep and the deep tide pool was 12.5 centimeters. For the temperature, the shallow was 22.9 degrees and the deep one was 19.6, so the deep tide pool was a little bit colder. And for the dimensions, the shallow tide pool was 24 by 20 centimeters and the deep one was 55 by 95 centimeters, so the deep tide pool happened to be a lot larger in size. And then the average distance moved for the shallow was 6.1 centimeters and for the deep one was 11.76 centimeters, and this gives a 5.5 centimeter difference between them. And when you look at the graph in figure 1, it just shows in orange the deep tide pool and blue is the shallow tide pool, and each snail, it shows how far each one moved from its rock. For my discussion, I read an article by Melnig that highlights intriguing behavior about periwinkles. Melnig's findings shed light on the dynamics of periwinkle population and their movement patterns, particularly in relation to their feeding habits. One fascinating observation Melnig made is periwinkles are algae consumers. This insight from this is that our discussion of why the deeper tide pools seem to have shifted over time. It appears that the abundance of algae in deeper tide pools attracts a higher concentration of periwinkles compared to the shallower ones. Consequently, these deeper tide pools become more crowded with snails, creating a competition for food resources. The larger area, the deeper tide pools, also means that food is more spread out and harder to come by, forcing the periwinkles to move around in search of food. This contrasts with the shallower tide pools, where there are fewer periwinkles and a smaller area to cover, making food more easily accessible without the need for extreme movement. Furthermore, Melnig points out that periwinkles in tide pools may also go onto the water or the edge of the rocks. This behavior suggests that snails have to move from the center of the deepest part of the tide pool. Periwinkles in shallower tide pools face much less of a journey with minimal incline, so what we can gather from Melnig's observations is it seems that the distribution and movement of periwinkle in tide pools are closely tied with availability of food. Deeper tide pools, with their abundance of algae and larger area, attract more periwinkles, but also have more movement to produce food. On the other hand, shallower tide pools offer easier access to food, resulting in fewer snails and less extensive movement required. This insight into the behavior of periwinkles is not only enhances our understanding of these creatures, but also provides valuable information about the balance of life within the tidal ecosystem. Some limitations that could be had was the periwinkles could have fallen or rolled into the pool after getting to the top, so they fell back towards the rock, or sleeping or resting. Also, environmental change can make them freeze with fear, or they could have been shocked after getting uprooted. In conclusion, Littorina, Littoriae, and deep tide pools do move further than ones in shallow tide pools. It's further to move to get to anywhere they want. If they want to get out of water, they're deeper down, so it's further. And it seems to be that there's more periwinkles in the deeper tide pools, making food shortages, so they must travel to get their food. For my acknowledgements, I'd like to say thank you to Isabel for answering any questions in every email that I sent, and to my mom, who helped me keep track and count the data for my experiment. I'd also like to re-acknowledge the Mi'kma'ki people and the Mi'kmaq territory that this experiment was conducted on.